Hello everyone. Today I am going to deliver a lecture on analysis of variance of one-way classified data for fixed effect model. This lecture is based on the syllabus of BSc CBCS 4th semester Statistics Honours Paper Linear Models taught in the colleges under Dibrugarh University. ANOVA for fixed effect model one-way classified data. If the treatments under consideration are the only level of interest, then the fixed effect or parametric model is used, which is given below as Yij is equal to mu I plus epsilon ij, which is equivalently written as mu plus alpha I plus epsilon ij, where I takes the values 1 to 3 up to k and j takes the values 1 to 3 up to ni. Here, Yij is the yield or response from the j sample having the ith treatment, and alpha i's are the unknown constants, mu is the general mean effect, and epsilon ij is the error effect due to sums. Now, assumptions for the model are as follows. All the observations Yij are independent and Yij follows normal distribution with mean mu I and variance sigma square. That is the constant variance for all Yij. The different effects are additive in nature, and the error effect, the epsilon ij, are identically and independently distributed normal variable with mean 0 and variance sigma square. That is, expectation of epsilon ij is equal to 0 and variance of epsilon ij is equal to sigma square for all I and j. So under the third assumption, the model becomes expectation of Yij is equal to mu plus alpha I, where I is equal to 1 to 3 up to k and j is equal to 1 to 3 up to ni. Then the statistical analysis of the fixed effect model. The null hypothesis will be like this. Here we want to test the equality of the population means, that is the homogeneity of different treatments. Hence the null hypothesis is given by H naught mu1 equal to mu2 equal to up to mu k is equal to mu, or equivalently alpha 1 equal to alpha 2 equal to alpha k equal to 0. Then the alternative hypothesis becomes at least two of the means mu1, mu2 and mu k are different. Then we may write yi dot bar, that is the mean of the ith class or having ith treatment. So this is equal to summation over I from 1 to ni, yij divided by small ni. Small ni is the total number of observations having ith treatment. So we have k number of means for k different treatments, where I takes the values 1 to 3 up to k. And y double dot bar, this is overall mean. This can be expressed as double summation Yij divided by capital N. Capital N is the total number of observations. So equivalently we can write it is 1 by n summation ni yi dot bar. Now the least square estimates of the parameters. The parameters mu and alpha I in the model are estimated by the method of least squares on minimizing the error or residual sum of squares as E is equal to double summation epsilon ij square, which is nothing but double summation yij minus mu minus alpha I whole square. So we minimize E by taking the partial derivative of the parameters mu and alpha I separately and making them equating to 0, we have two normal equations. So the first normal equation is del E del mu equal to minus 2 double summation yij minus mu minus alpha equal to 0. And the second normal equation is del E del alpha I is equal to minus 2 summation j from 1 to ni yij minus mu minus alpha equal to 0. So from the first normal equation, after simplification, we have mu cap equal to 1 by n double summation yij. This is equal to nothing but the overall mean y double dot bar. And from the second normal equation, after simplifying, we get alpha cap is equal to yi dot bar minus y double dot bar. This is the mean of the ith treatment minus the overall mean. So by substituting these two values of mu cap and alpha cap in the model, we have yij is equal to y double dot bar plus yi dot minus yi dot bar minus y double dot bar plus yij minus yi dot bar. So here the first term yij is nothing but the observation. Then y double dot bar is the grand mean. Yi dot bar minus y double dot bar is the deviation due to ith treatment. And yij minus yi dot bar is nothing but the residual or error component. Then the partitioning of sum of squares. Error component epsilon ij is introduced so that both the sides are equal. This is the deviation within the class which is due to the randomization. Now we have yij minus y double dot bar which is equal to yij minus yi dot bar plus yi dot bar minus y double dot bar. So here you see, you can cancel this yi dot bar minus yi dot bar plus yi dot bar, and we have yij minus y double dot bar. So you take the squares of both sides and take the summation for I and j. So here in the left side it is double summation I from 1 to k, j from 1 to ni, yij minus y double dot bar whole square, which will be equal to double summation I from 1 to k, j from 1 to ni, yij minus yi dot bar plus yi dot bar minus y double dot bar whole square. If you treat the yij minus yi dot bar as the first term and yi dot bar minus y double dot bar as the second term, then it will be the a. Suppose this is a, second one is suppose b, so a plus b whole square. So you can expand it by the a plus b whole square formula. You have, this is the a square, this is the b square, this is the product term 2ab. Thus we have double summation yij minus yi dot bar square plus summation I from 1 to k ni into yi dot bar minus y double dot bar whole square plus the product term. So in the product term, you see summation I from 1 to k yi dot bar minus y double dot bar, this is equal to 0 because the sum of the deviation of observations from their mean is always equal to 0. So this product term will be vanished. So after putting 0 in the product term, we have summation I from 1 to k, summation j from 1 to ni, yij minus y double dot bar whole square. This is equal to the 2 square term. That is summation I from 1 to k, summation j from 1 to ni, yij minus yi dot bar whole square plus summation I ni yi dot bar minus y double dot bar. So in this expression, the first term in the left hand side is the st square. It is termed as st square, means the total sum of squares, TSS. And in the right hand side, the first term is denoted as SE square. This is capital S, capital E square. This is called the within sum of squares or error sum of squares. And the last term in the right hand side is denoted as capital S small t square. And this is nothing but the sum of squares due to treatment, SST. Thus we have total sum of squares is equal to sum of squares due to errors plus sum of squares due to treatment. Then degrees of freedom for various sum of squares. The ST square, capital T square is the total sum of squares, which is computed from capital N quantities of the form yij minus y double dot bar and will carry capital N minus 1 degrees of freedom. Here, one degrees of freedom being lost because of the linear constraint double summation yij minus y double dot bar equal to 0. Similarly, for the treatment sum of squares, capital S small p square, this is equal to double summation ni yi dot bar minus y double dot bar square. It will carry k minus 1 degrees of freedom because the one degrees of freedom being lost for the constraint summation ni into yi dot bar minus y double dot bar equal to 0. And for the arrow sum of squares, we get n minus k degrees of freedom, since it is based on capital N quantities and which are subject to k linear constraint. They are summation j from 1 to ni, yij minus yi dot bar equal to 0. Thus, we have a constraint of this type where I takes the values 1 to 3 up to. Thus, we see that the degrees of freedom for various S's are also additive. That is, n minus 1 is equal to n minus k plus k minus 1. So here this is the degrees of freedom for total sum of squares. Then n minus k is the degrees of freedom for arrow sum of squares. Then k minus 1 is the degrees of freedom for sum of squares due to treatment. Then mean sum of squares, that is MSS. The sum of squares divided by its degrees of freedom gives the corresponding variance or the mean sum of squares MSS. Thus, the mean sum of squares due to treatment is obtained by SST divided by k minus 1, that is small s small t square. The notation is small s t square, and then the mean sum of squares due to error can be obtained by SSE divided by n minus k. This is denoted by small s e square. Then the test statistic. The test statistics is here F statistics, the variance ratio. So F is equal to small st square divided by small s square. So if h naught is true, then F should be take the value 1. And otherwise it should be greater than unity. Thus, if an observed value of F obtained from this expression is greater than the tabulated value of F for k minus 1 n minus k degrees of freedom at specified probability level of significance, and usually it is 5% or 1%, then H naught is rejected at that level, and otherwise we fail to reject the hypothesis H naught. So this statistical analysis of fixed effect model for one-way classification of data can be presented in the following analysis of variance table. This is the analysis of variance table for fixed effect model one-way classified data. Here there are 5 columns. First one is the source of variation. Source of variation is split up into treatment, error, and total source of variation. Then the second column is the sum of squares. This is the for treatment. This is sum of squares due to treatment. Then sum of squares due to errors. Then total sum of squares. The third column is the degrees of freedom. For the treatment, the degrees of freedom is k minus 1. Degrees of freedom for error is n minus k. And degrees of freedom for total sum of square is n minus 1. Then mean sum of squares for treatment is small st square is equal to sum of squares due to treatment divided by k minus 1. Then due to error is sum of squares due to error, mean sum of squares due to error is sum of squares due to error divided by n minus k, the degrees of freedom for error. Then the variance ratio F can be calculated as small st square by small s square, and this F follows F distribution with k minus 1 and minus k degrees of freedom. So this is the analysis of variance table for one-way classified data for fixed effect model. So dear student, I conclude today's lecture here. Thank you.